Okay, so we had a couple kind of things we could look at. There was this whole notion of really going through and being able to go ahead and bias this in some way so that we could go through and change it around, actually add some different variables to start incorporating different values and kind of do something like that. So, for example, if we were looking at this example and we actually wanted to say that we had some notion of a targeted floor area or some sort of notion of the surface area where we wanted to go through and compute things a little bit differently, there's a number of ways we could do that. We could do the calculations either in Dynamo or we could do the calculations right in Revit and let Revit act as the calculation engine. In a lot of ways, it's nice to let Revit act as the calculation engine because as we do that, we can take advantage of the material or the information about the materials that's actually in Revit. So for example, if I was going to go through and just start defining some things, for example, if I had a roof area that was going to be defined as an area, okay, where that roof area was going to be, what would that be? That'd be just width times, the depth. Okay, if we also were going to go through and define some sort of wall area, and the wall area we can define in a couple of different ways. Yeah, we could say that it's going to be, 2 times, I'm just going to put this in a nice kind of parenthetical structure, 2 times the height times the width. See if it'll like that. It might not like that because, nope. It's actually quite picky about the way I go through and capitalize things. Plus 2 times the height times the depth. Okay, let's see how that actually looks. Inconsistent units. Oops. Yeah, I think if I go through, it's complaining. I bet it is having troubles because as I've gone through and defined the parameter, I probably didn't click the area checkbox. Let's just take a look at that. Yep. It's hard to change the type of something like that after the fact, so what I usually end up having to do is remove it and add it in again. I'll put it in the analysis results again. So it's going to be wall area. So watch out for that as you set things up. Instance parameter. Oops, come on you. Make it an instance parameter. I didn't quite catch that. Okay, so this again is going to be 2 times the width times the height plus 2 times the depth times the height. Again, this is just going to work for this very simple structure, but it'll get us going. Okay, now we can go through and say that there's some sort of total area. And I'll even call it the total weighted area. Because this is where I can go through, and it's going to be an area. Let me get that right for you. It's going to change on an instance by instance. This is where we're going to want to add that weighting factor. And we can do this weighting factor by manually putting a number in here. A smarter thing might be we might actually go ahead and get the weighting factor based on the thermal conductance of the wall surfaces that we're actually reading right out of the Revit model. We'll get to doing things like that. So I could say that it's going to be 4 times the wall area plus, and I can just be really explicit, if the weighting factor is 1 for the, actually, I take that back. What I decided to do was I wanted to make the wall area a factor of 2 and the roof area a factor 1. That's just sort of allowing the walls to have about twice the thermal loss as the roof. But again, these weighting factors that I put in there, we could really use whatever seems to make the most sense based upon what we could read from the actual value. So in this case now, total weighted area is the thing that's interesting to me. So with that, And let's load that into the project. What I can do is go back and in Dynamo, change that same like a script so that it optimizes based on the total weighted area instead. Okay, so to do that, again, I'll go back to Dynamo. Let's see if I still have it open in the background here. I think I do. Not the App Store. Let's close that up. Okay, so bringing up Dynamo, if I want to get the total weighted area again instead, what I can do is just back over here in my script, say that as opposed to optimizing the gross surface area, okay, I want to get the total weighted area. Let's just kind of make sure that we have that. We'll come back over here, say total weighted area. That looks like one of my instance parameters. So I should be able to come over here and just say that our parameter to report, in this case is what I'm optimizing by, is the total weighted area. Take out that return. Beautiful. And now if I go through and run this, we'll instead just look at a different series of values. It's going to go from 20 all the way to like 200, but it's going to be optimizing that total weighted area instead. Okay, that's really the idea behind all this in terms of being able to kind of quickly run and kind of look at these. I'm sort of curious about how different this will come out. I think the last one, it turned out to be about 120 was the optimal value. Let's see what it comes out with here. So the idea is that really it's all about trying to use the Revit model, the Revit parts, the Revit families, and the properties that are being read out of the model, and use that for doing the optimization. Okay, it's going to go through and do its calculations. That's going to be just fine. As it's doing its calculations, if you want to kind of look ahead to where we're going next, you could even look at and try playing around with its example 12.3. Just being a little slow, we'll see what the result is. 12.3 is actually, it's an example of, it's the parametric twisting tower. It's a little more interesting than just the notion of just kind of looking with these little rectangular boxes, which are pretty easy to calculate, because the parametric twisting tower, which is based on that triangle shape, has an unusual form. It's really actually rather hard to compute the area of any individual floor based on the parameters. You really almost have to use the geometry to go through and generate that. So, we're up to 130. I'm going to let this finish running its way out just so we can sort of see what the final result is on this, but open that up. The interesting thing about the parametric twisted tower is we could do some sort of similar optimization with that, where you have a height variable, you have twist, you have the whole idea of the width of each of the different floors, and we could go through and construct some sort of interesting ratio between those different things to, again, try to figure out really what the optimum surface area is or the optimum height based on the surface area, really whatever it is that we have in mind. Okay, let's go ahead and up to 180. Let me get it up to 200 and see what this actually comes out to. I'm quite curious. Okay, looks like 60. Interesting. So if we looked at the values in there, we could actually get to really why the total weighted area of 109,000 is actually best in terms of the areas that we do consider, and especially weighted for what we think the thermal or the relative thermal conductance of those would be. Go ahead and close that up. Just kind of open that 12.3 just as an example, and just give you something to think about for next time. I'll say, sure, let's save that project. Okay, in terms of 12.3, one of the only differences that's an extension of what we've looked at so far is, going to open it up. Let that flash around a little bit. It's kind of a more interesting shape in that it has different parameters for the height and the rotation and the twist and kind of the width at the height and the midpoint and things like that. One of the few things that's a little bit different though about it is that we've actually taken the mass and we've divided it into mass floors. Okay, now that example 12.3 is open up, let's take a look at the special part and see what we have available. So if we click on the mass form that's loaded into this example, you'll see that we actually have a number of different instance parameters available to us. We have the top height, the rotation at the top, the radius at the top, as well as at the midpoint, and even the base. So we have a lot of flexibility in terms of flexing this and checking out different values and being able to use data about this form as part of our calculations for optimization. Now, one new value that's available that's a little bit special is the gross floor area. Let's talk about that and where it's coming from. So if we choose the mass, you can see we have a gross floor area computed. Where that's coming from is actually mass floors applied to the mass. So as we did in 120A, we've taken that mass and divided it up by a series of different floor levels. And based on the total number of floor levels there, okay, it's at each of the different levels, going through and computing that floor area just based on the precise geometry of the form. So at each of those different floor levels, it's computing the floor area there. And the nice thing is, as we look at flexing this overall form, if we change its parameters, that gross floor area is going to continue to update and change for us. So for example, if I change that instead to be, 600 feet tall, add another 10 floors to it, you'll see that the gross floor area is going to go for 212, 649. Let it do its recalculation. As the form is reshaped, it's going to create a lot of new mass floors to fill in those last 100 feet that we just added. So our gross floor area has increased to, oops, I can select that again. To 254,000. Now, that would also change if we changed any of the radiuses, if we changed the height parameter in terms of the banding, that would change. If we change the twist, even the amount of rotation, again, that gross floor area would change. So we have a lot of different variables we can start playing around as we start trying to optimize this form and really immediately see what the impact is on the gross floor area. And this is what we want to start thinking about tying together, is how we can kind of bring those things together and then ultimately use that to try and derive some new optimums. And that's really what we're going to be doing in the next class session. So let us adjourn for the day and go ahead and just get ourselves started for next time. So please get yourself started on assignment 3. See if you come up with any interesting questions you want to address in class next time. But I'll look forward to seeing you on Thursday. Okay, thanks, and we'll see you soon. Bye-bye.